SS. Although a modern agent, it has sedating side effects also. So it also has sedating, clemastine also has sedating effects. And it's quite different. So again, I hope what we need to look at is to understand even those things that I have not mentioned, like the influence of a pyridyl group, the influence of a substitution or para-substitution, if I have not mentioned. All those things that we have mentioned, the two aromatic rings, the alkyl chain, the dimethyl amino group, it being tertiary and all those points are relevant for these drugs. And that is why we started with them as generous, so that you understand they relate to all these drugs. Of course, with such differences, like now you have seen clemastine has some slight, we have mentioned clemastine, and we have said there is some slight. It has its own, not difference, but it has its own uniqueness. It has its own uniqueness in that it has two chiral centers, and of course, we have also said it has all its own uniqueness in that one of the carbon atoms is part of a pyroridine ring. So those are the uniquenesses that you find in different groups. In some of the groups, stereochemistry does not matter. Like we did not mention, there was no stereochemistry with the ethylene diamines. But when now you come to the ethanolamines, stereochemistry indeed is of very great importance. Again, the synthesis. They are used, these drugs are used again in mild local allergic reactions, just such as allergic rhinitis and allergic conjunctivitis. Also have antiemetic and antitussive properties. Those are some of their uses. Of importance to note is that the oxygen that we have, we cannot replace it with any other atom. Of importance to note is that unlike the bioisosteric oxygen to nitrogen atom replacement, conversion of the oxygen atom to a sulfur atom in the diphenhydramine series results in a compound with greatly decreased antihistamine activity. So we are saying that unlike the bioisosteric oxygen to nitrogen, of course, when you change it to nitrogen, that's where we get the ethylene diamines. But you cannot change that with sulfur. If you do so, the resultant compounds have almost no activity at all. Metabolism, I'll look at metabolism, I'll look at it at the end. The alkylamines or the propylamines, these are the most potent and widely used. That's why you find chlorpheniramine, which I said is Piriton, a very abused drug, abused even with children. When you have a very irritating child, some people prefer to give Piriton or chlorpheniramine for that child to sleep. A story is told, I don't know whether it is true, of how one house girl gave too much, and indeed to the extent that it was very toxic to the little one. I think was the girl had a lot of things to do. She had better things to do, so, and the child was very irritating, so they gave them Piriton to sleep, because as we have said, one of the side effects of these drugs is sleep. So, and sometimes the sleep can be taken as a positive effect. Like if you have somebody with a lot of itching all over, if you give them the chlorpheniramine and they can sleep a bit, it's good for them, because it will the discomfort in terms of itching. So that negative effect can also be considered as positive effect. So the alkylamines, propylamines, most potent and widely used, characterized by a long duration of antihistaminic action, decreased incidence of central sedative side effects compared to the ethylene diamines and ethanolamines. So they have lesser sedation. Introduction of chirocarbon when the two aromatic rings are different. Again, most of them have the pyridyl, not all of them. Like you see, pyrobutamine does not have a pyridyl, but most of these drugs have a pyridyl ring. And once the two rings are different, then of course there will be chirality, and the S isomer is more active than the R isomer for this class again. So we have the examples: pheniramine, and you can see what I'm saying. You have that is pheniramine, chlorpheniramine, and that is brompheniramine. Most of them, as I've said, with the exception of pyrobutamine, have that. So you can see pheniramine, that pheniramine. So that's a prototype, And then chlorpheniramine, we are just using the same SAR para substitution of the other ring. Brompheniramine, again, substitution with that. And then triploridine. Remember, we did mention triploridine is where you have unsaturation, and triploridine is like clemastine, where you have the pyroridine ring. So therefore, if you look at this, you can see this nitrogen is completely out. So 1, 2, 3. So all the carbon atoms are out. There's none which is part of the ring. It's only the nitrogen which is part. So here, it is only the which is part of the tetracyclic ring with retention of activity. But in some of the others that we have looked at, they're like where clemastine, also one of the carbons, is part of the ring with retention of activity. The phenylpyrarine, but all the carbons are part of the heterocyclic ring with retention of activity. And then, of course, we have also phenidamine. And as if you look at phenidamine, it is where these are two phenyl. That is the phenyl ring. That is the other phenyl ring. So we are going 1, 2, 3. So again, in this one, it was also an example of where the carbons, again, the carbons are part of actually a tricyclic ring. Here they are part of a tricyclic ring, again with retention of activity. So we have the phenyramine, chlorpheniramine, brompheniramine. Please note the difference between this and the others is the unsaturation. It's going. Synthesis. So if you look at propylamines, phenylamine is a prototype, as we have already said, and is the weakest member. It is the weakest member because we did mention it has no substitution. When you substitute, para substitution, as we have said, or para substitution increases activity. Halogenation as the para position increases potency significantly, such as chlorpheniramine, a very, very good antihistamine. Is 10 to 20 times more potent, yet with no significant increase in toxicity. Remember, we have said that chlorpheniramine has minimal CNS activity. Brompheniramine is slightly more potent, but with a half-life almost twice as long as chlorpheniramine. So again, brompheniramine has longer activity, but the one which is most popular is chlorpheniramine. Remember, the chloro group is part of our bodies. So when you have a drug with a chloro group, you do not expect a lot of issues. The drugs are chiral. The S isomers have greater binding to the receptors for the propylamine. So note the S isomer have greater binding to the receptor. The phenylamine is marketed as a racemate mixture, but chlorpheniramine and brompheniramine have been resolved and are marketed both as a racemate and in the more active S-dextrorotatory isomer. You have, so we are saying like for phenylamine, you give it as a racemate mixture. That means the S and R isomer. But for propylamine, even you have one, which is a pure S-dextrorotatory form, and the levorotatory form, the R levorotatory form, which of course you not get the R, you not get the R levorotatory form because that is the one which is less active. So you have it in the more active S-dextrorotatory form, and you have it in the market. But if you go for the S-dextrorotatory form, it will be more expensive. I think it's what we call proramine. Quite expensive because, of course, it's the resolved. It is the pure isomer, therefore a little bit more expensive. But it, of course, will have better activity. In this class, isosteric replacement is limited. Only the phenyl and the 2-pyridine are allowed. Any other replacement results in a decrease in activity. And indeed, if you look at those drugs, as I said earlier, we do not have like the other classes where we had the thionate, we had the pyridine ring, we had the pyrimidine ring, and we had the benzyl ring. In these drugs, you only have the pyridyl ring. The pyridyl ring. You only have the pyridyl ring. You do not have the several aromatic rings that we can find, or which we find in the other drugs. If you do put the other rings, so they were found to be responsible for lower activity, and therefore there was no need. Whenever you have a substitution which brings a lower activity, then you leave it out. Remember, most of these are developed slowly through clinical trials. So, of course, initially using animals, so you change the structure, you do clinical trials using the animals, and you look for the structure which is responsible for the highest activity with minimal toxicity. Triploridine and pyrobutamine have unsaturated, they have unsaturation in the propylamine side chain and therefore exist as geometrical isomers. So here again, here we have some difference. So remember we did mention, we have already said we have said that the triploridine, if you look at its structure, it has one of the rings is a pyridyl ring. The other one has a para substitution in the methyl group, which we have already explained. Para substitution in the methyl group, we had said earlier, of course, also will increase potency. But now when you look at this compound, it has that double bond there, and that double bond, so that means we have a hydrogen coming up here. So you can have both the E-triploridine and the Z-triploridine. Remember, the E is the trans and the Z is the C. So you can have both isomers. You can have both the E-triploridine and the Z-triploridine. And it was found that in both cases, the E isomer is more potent. So you're only saying that it was found that the E isomer, and of course the E isomer, as we have said, the E, see this, where the big groups, this is the one of the big groups, and this is the other big group. They are on opposite sides. So the E isomer or E-triploridine was found to be more active, and we can expect that to be possible. The E represents the trans isomer, and the trans isomer we know is the isomer which represents which has much lower steric hindrance because the bulky groups are on opposite sides. So triploridine and pyrobutamine have unsaturation in the propylamine side chain and therefore exist as geometrical isomer, and in both of them the E isomer is more potent. So this is pyrobutamine. But incidentally, when I look for the structure of pyrobutamine, some of the books it is not showing this pyridyl ring. I will look for it again to confirm. But in some of the structures I've found, they are not giving a pyridyl ring, but I'll confirm again whether we have that pyridyl ring. So when for both of them, again, remember, you have the pyroridine ring, and all we are saying, so for pyrobutamine, you can see pyrobutamine defiles the structure of these compounds, because unlike the other compounds where we have said normally we have the benzene and the pyridine and the pyridyl ring, pyrobutamine incidentally has the benzyl ring, and that makes it different from the other compounds. So for the unsaturated compounds, it has you have pyrobutamine, which has the benzyl. Saturated compounds, you do not have any of the compounds with a benzyl ring. It's just a phenyl and a pyridine ring. But for pyrobutamine, it was found that that ring could still give us activity. But as I have said, I want to confirm, because quite a number of the structures I've looked at, I want to confirm. I think this is a mistake. This is supposed to be a benzene ring. But let me confirm, but I'm sure it is a mistake. It's supposed to be a benzene ring and not a pyridyl ring. And now we are saying here, again, this compound will have stereochemistry, and here stereochemistry, and we are still saying the E isomer is the most active. The acrivastine, that one is not in this group, so we will not discuss it now. Alkylamines, the alkylamine have significantly less CNS depressant effects and the benzhydroethers than the ethanolamines. These compounds have long half-lives and extended duration of action, have decreased antiemetic effects and decreased anticholinergic properties compared to the ethanolamines, and dealkylation is a major pathway. The corresponding secondary and primary amines as parent drug being found in the plasma. We look at the metabolism, and as long as you have drugs that have dimethyl amino groups, oxidative N dealkylation or demethylation will be one of the root of metabolism. But we look at metabolism much later. So those are the propylamines. As I'm saying, once you need to understand, once you understand the general, the general SARs, then for sure you understand this compound. This is just showing us distance between Z substituents. This is just showing us the stereochemistry here, that it was found, we have a distance between the E substituents, potential binding sites based on E and the Z configuration. All we are saying is that once, depending on which configuration you have, of course, you have the configuration whereby the two rings, like now for this one, this ring is more bulkier than this one because of the chloro group. So that ring is more bulky than that one. When you have the pyridyl ring will be more bulkier than a group like this one. So we are only saying that when you have these compounds, you find that, of course, the Z and E isomers will have differences in their distance. You remember we talked about the distance that you require. So they have differences in their distance, and it was found that it is the E conformer that gives you the necessary distance that you require for activity. So you can see this is telling us the distance between the E substituents. That is this one. This is the bigger ring, and that is a bigger ring. So that's the distance between the E substituent, distance between the Z substituent, that is that one and that. So when you have this kind of configuration, this is the huge one, and this is also the huge one. So we are looking at this distance, the distance between this group and this group. And then this is the smaller one, and this, of course, is a huge group. So that this is the Z means it is a cis. So this is the cis, the big group. This is a big group, but this, of course, will be the smaller group. So they're saying this is the distance between the Z substituents. Those are the cis substituents, the ones which are adjacent to each other. Yeah, I see what they mean. So when you look at these drugs, the way they have arranged, it is such that this group and this group are, to me, they are on the same side. This group on that, because the hydrogen will be on this side. So this hydrogen here, this hydrogen is a small group, and this is a small group. So this hydrogen, which is a small group, is on the same side with that. Then this group, this hydrogen there, the same side. Then this substituent here is a big substituent, and this other substituent here is a big substituent. So in this particular one, they have drawn the big substituents, both the pyridine and the chlorophenyl group are on the same side. So that's why they're saying this one is a big one, that is a big one. This still is the big one, and that is a small one. So what are they trying to show us? They're saying distance between E substituents. The E substituents are the ones that are responsible for the trans isomer. The E substituent is what we get with the trans isomer. When we talk about the trans isomer, we say that is when this group and this group are different. So I think what they are just trying to show is that if you have the E isomer, the substituents, the E substituents, because of the fact that not necessarily this one, they're just giving this to show the group. So if you are to look at the distance between the E substituents are the ones which are responsible for the trans isomer. You'd expect, because of the fact that the bigger groups are farthest from each other in the E isomer. Remember, the E is the same as the trans, and the trans means the groups, the big groups, are on opposite side. You'd expect that those groups, the distance to be much shorter because of the fact that there is less steric hydrons. When you have the big groups on the same side, those two big groups must repel each other, and therefore the distance between the two groups, because they have a lot of steric hydrons, that distance will be very, very big. The diagram is not very clear, but the way I understand is that all they are trying to show us is if you have the E isomers are formed when you have groups farthest from each other as possible, on opposite side. The E isomers are formed when the large groups are on opposite sides. And when the large groups are on opposite sides, you have lesser steric hydrons, and therefore you have your molecule being much smaller, because there is less steric hydrons, and the molecule can be able to penetrate the receptor. When you have the big groups being on the same side, those big groups must be separated by a larger distance. Why? Because they have steric hydrons. When they're on the same side, they will be repelling each other. You have two big groups, they must repel each other, and therefore, in the Z isomer, where the big groups are on the same side, you expect that the distance between the two groups is much, much larger. And because it's much, much larger, it will not allow for the 5 to 6 angstrom for binding the receptor. And that supports why that is the support we have for the fact that the active isomer is the E isomer, which is a trans isomer, where both the big groups are on opposite side, allowing that molecule to be a bit condensed, allowing that the molecule to be a bit condensed to give you the correct measurement of between 5 and 6 angstrom to be able to bind the receptor. So this is just showing us that depending on which conformer you have, the distance within the molecule will be much larger when you have the Z isomer as compared to when you have the E isomer, and therefore the E isomer is more preferred. It's more preferred for binding. So we have now done up the propyl alkylamines. I'm first of all leaving what is in the middle because I'll introduce it later at its own due time. It's not yet. When you're looking at the second generation is when we look at that. Any questions so far? Any question, class? Any questions? Are we okay? So there are the general SARs that apply across the board, as I have said. But when you look at the specific structures, depending on the structure you are looking at, and we have given examples, depending on that specific structures, there are other characteristics that can come up. You can have stereochemistry. You can have, as we have just discussed at the end, with the alkylamines, you can have geometric isomerism. And the geometric isomerism, which will not be found in all compounds, where need be, and you have the geometric isomerism, then you will have another SAR, which is very important, whereby you must remember to mention that the big groups, that the compound that is responsible for best activity will be the E isomer. And you can be able to explain, because in the E isomer, the big groups are on opposite sides. And because they are on opposite sides, they reduce these steric hydrons, and therefore the molecule within the molecule. If you have a lot of steric hydrons within the molecule, then you must apply a lot of energy to retain that molecule at the appropriate size, and therefore it will be a very unstable molecule. But when these big groups are on opposite side, there will be less steric hydrons, and therefore that molecule can still try to attain the necessary size, 5 to 6 angstroms, to be able to get to the receptor. When it comes to the other one, for those molecules that have stereochemistry, again, remember the stereochemistry is the arrangement of these drugs in space. There will be that arrangement. There will be that arrangement that allows that molecule again to have the correct size to bind the receptor. And that's why for some, we are saying like carbinoxamine, it's the S isomer, S-dextro isomer. That gives you the right size. When we come again to the clemastine, we are saying the R isomer is again the best, the needed size. Now, when we come again even to the propyl, the alkylamines, again we are saying the dextro isomer, S-dextro isomer again is responsible for the correct size. So all we are saying is in the stereochemistry. The stereochemistry is as a result of the fact that the molecule must have the right size, 5 to 6 angstroms between the central atom and the terminal nitrogen, for that molecule and access the receptor and attach itself to the receptor. If the molecule is too big, it cannot fit the receptor, and therefore will be having a poor fit. Once it has a poor fit, that is why one of the isomers will have the lesser activity than the other one, because one of the isomers has the right shape that acquires the right size for it to be able to access the receptor appropriately, to have the best affinity receptor and bind it to the receptor. I think we'll end there. At least I think we'll be able to finish these ones, I hope. Next. I've done, I think, the bigger groups. Actually, what is left now is from the groups now that are remaining are smaller ones. And again, we had to, since I've done the introduction and introduced all the general SALs, then it will be much easier to be able to go through the other groups. So I think in another, we're almost there. Almost there, not very far. You should be able to finish on time. Any questions? Any questions, class? Ndio mko quiet sana. You were also very few. I think maximum we were 28. I hope the others are not reading for a cut, because even if you read for a cut and pass your cut and fail the main exam, it is more critical to pass the main exam than the cut. But anyway, we all have different ways of looking at what we do. I think with that, we can have the usual. Please kindly show in whichever manner, indicate your presence in whichever manner possible, either a yes, present, a thumbs up, whatever. It's always important, because that is what I use as my attendance list. That's what I use as my attendance list for every class. I hope we are okay. If there are any questions, please raise them. And I wish you well. The cut is not hard. It's an easy cut. If you have read well, it should be at 3 o'clock. Please try not to cheat. That is my request, my humble request. Try not to cheat.